In this video, I'll be explaining about basic solutions. In my last video, we have given a definition to basic solution. I have also done some of the example to understand what is basic solution. Now let us continue our discussion a little more deeper towards the basic solution. So we have considered a system AX equal to B. To do this equality, I have introduced slack and surplus variables. So if the constraints are involving inequality, introduce slack and surplus variable to make them equality constraint. And A is a matrix of order m cross n. And we also know that the rank of A is equal to 1. So at this moment in the definition, I am assuming that the rank of A is equal to m. So if I put n minus m decision variable equal to 0, then the system is reduced and the solution of this system is called basic solution. In addition to this reduced system, if I also take that the decision variable are non-negative, which is usually given in the linear programming problem, then we call this as basic feasible solution. So if the decision variable in basic solution that we have solved are all non-negative, then it is called basic feasible solution or BFS. And if basic solution have at least one variable with the negative value, then we will call this as infeasible basic solution. Now let us take the definition to one step further. We define degenerate and non-degenerate basic solution or basic feasible solution. To understand this, let me to consider an example. Consider a solution capital X which is dependent on 4 decision variable, and at this stage I am assuming these two as basic variable and these two as non-basic variable. Now because these are non-basic variables, so their value is certainly 0. This is how we started assuming in the definition of the basic solution. And these two I am going to find from the question. This is the reduced system. Suppose that this value is 2, 3, or suppose this value is minus 2, 3, 0, 0. Or I may assume that this value may come at as 0, 5, 0, 0. Now let us specifically define. If both the decision variable are positive, they are not 0. So this falls in the feasible category. This is basic feasible. If they satisfy non-negative restriction, they are not negative. If one of the basic variable is negative, this is infeasible solution. If one of the basic variable is equal to 0 or positive, so they are non-negative, so they are feasible, they are basic feasible, but in addition to that, they are also degenerate. So this is called degenerate basic feasible solution if one of the basic variable also take the value 0. There are non-basic variable which were 0, which is fine. But if the basic variable takes a value 0, it is called degenerate basic feasible solution. And if both of them are not equal to 0, basic variables, then we set this as non-degenerate basic feasible solution. And finally, we can define optimal basic feasible solution. After finding all BFS from all the cases in a particular question, we will choose the one BFS that optimize, maximize or minimize the objective function value. That will be called as optimal basic feasible solution. And because we are talking feasible, so feasible means we have to always keep in consideration the non-negative restrictions. So now my objective is to give you the connection of graphical and algebraic method, or I may say connection of corner point and basic feasible solution. Corner point that we have found from the graphical method while solving the question with the graphs, and BFS we just have defined. And second, I want to verify this inequality, that vertices or the corner point are always less than or equal to BFS, always less than or equal to basic solution, and it is always less than or equal to NCM. What is this NCM? NCM, because we have said that A is a matrix of order m cross n and the rank of the matrix A is m. So we can always choose basic variable as m and the remaining is non-basic variable as n minus m. So out of n total variable, we are choosing m basic variable. So that means total basic solution cases could have been made as NCM. So we will see why this inequality hold in the examples. And finally, we can talk about optimal solution in the problems. So let us consider one example to explain the first case. So in this problem, we want to write all basic solution to the following system and find the optimal solution as well. So I am explaining the third point simultaneously while addressing to first and second objectives. So we can see that in this question, the constraints are less than. So here I want to add a slack variable S1 and S2 in the first and second constraint. So I have written adding slack and surplus variable wherever they are required. So in this question, we only require slack variable. Once we've solved the slack variable, this is the same problem I have taken in my last video also. So we can make cases, there are basic variable selection and then there are non-basic variable selection. So we know that whenever we select non-basic variable, this value is always equal to 0. So assuming that these both variable value is 0, we are going to reduce the system. So I'll give you the first case. So when I've taken that S1, S2 as basic variable and X1, X2 as non-basic variable, so these two value is 0. From the constraint which is given by star, so we have the first constraint 2x1 plus x2, and obviously because here I have added a slack variable, so this is plus s1 equal to 4, and then the second constraint is x1 plus 2x2 plus s2 equal to 5. Now when I take x1, x2 equal to 0, so these two values are gone, the value 0. So from here I get s1 is 4 and s2 is equal to 5. So we got 4, 5 as the basic solution. And similarly, while taking these cases and substitute that into the constraint star, we get all these solution. From here now I have to also choose which is basic feasible solution, because for finding the optimal solution I must always need to include my non-negative restrictions. Now in this non-negative restriction we are going to reject this negative sign. So just reject this one because there is a minus 3. We also reject this one, as we can see. These are not feasible. The remaining are feasible. So those which are feasible, now substitute those feasible in the objective function. What is the objective function here? Objective function is, we want to maximize z, that is 2x1 plus 3x2 plus 0 into s1 plus 0 into s2. The cost of slack surplus variable are 0. They are only included in the linear programming problem so that we can solve this system using the system of algebraic equation. Now look at in the first case again. In the first case x1, x2s are 0. Their value is 0. So this value is a 0. And in the first case s1 variable value is 4 and s2 variable value is 5 that we have solved. So this is 0 into 4 plus 0 into 5. Now whatever is the cost of x1, x2, because these values are 0, so the total z value is 0. This is what is written here. Now in the second case we do not need to check because it is a non-basic case, so I have not calculated the value for z. But look at the third case. In the third case x1 is a 0, it is a non-basic, and s2 is also 0. So these two values are gone, but it depends upon x2, s1. So but s1 cost is also 0, so it finally depends on only x2. x2 is 2.5, so 3 into 2.5, and the value for s1 we can even put this is 1.5, although it doesn't make a difference. So this is 2.5 into 3, so this value is 15 by 2, and 15 by 2 will give me 7.5, and that is why I have written here 7.5. So we substitute now these values one by one in the objective function and we find these values of the z. Now simply compare from here and we can see that z equal to 8 is optimal. So that means this is my optimal solution. So I can write in total z value is 8. This is maximum. This is a maximization problem at x1 is equal to 1 and x2 is equal to 2. So that's the optimal solution we got from the basic solution or the algebraic method. Now look at the same problem again through the graphical method. So we have drawn the graph of the constraint, first constraint, and the second constraint. So here I have drawn the first constraint. This is the second constraint. Because these are the line that we have drawn and then we identify the region. So at the line we can notice that at the first line s1 variable is equal to 0 and at the second line s2 variable is equal to 0. These corner point which are now the part of the region, let me to call this as A. Here this value is B, this value is C, and here this value is D. A point is 0, 0. B point is 0, 5 by 2. We can see it from the constraint when we draw this constraint. C is 1, 2 and D value is 2, 0. And this is the feasible region. Now what we are saying is that there is a connection of the graphical corner point and basic feasible solution. So we have a one-to-one correspondence between these. How many BFS we have identified from the question? 1, 2, 3, 4. So there are 4 basic feasible solution and we can look at the graph. There are 4 corner points. Now this shows that there is a one-to-one correspondence. Now I want to match also the value of the point. Now here whenever we say that this is 0, 0. At this point when x1 is 0, x2 is 0. From the system of the star you can rewrite this as a constraint less than or equal to 4 x1 plus x2 2x2 less than or equal to 5. So if I convert now the system into equality and I write s1 equal to 4 plus s2 equal to 5, and corresponding to this corner point, whenever x1, x2 is 0, obviously s1 is 4, s2 is 5. This will allow me to get this point, the first point that I have identified from the BFS. Look at the second corner point. In this second corner point, at this line, I have already seen that s1 is 0. x1, x2 you already know. I only need to find s2. So from the second constraint, you can see that if x1 is 2 plus 2 times x2 value is a 0 plus s2 equal to 5. So what is the value for s2? s2 is 5 minus 2. That is the value, that is 3. So this value when d is 2 comma 0. So the s2 value is 3 here. You can see that s2 variable is 3. So this point is exactly same that is shown here at the corner point. Look at it, the third case. In the third case, we see that it is the intersection of the lines, and here s1 is 0, s2 is 0. So this point, C point, is this one when x1, x2 value is 1 and s1, s2 is 0. Last corner point, this value is b, 0 comma 5 by 2, and similarly we get this last corner point, which is this one, and we can find the corresponding value by the questions. If you want to identify from the graphical to corner, convert this into equality. We have found the corner point. For each corner point you substitute back into the equality system, you can find the slack surplus variable value. So we see that basic feasible solution and corner point are equal. We have mentioned now this in the inequality that vertices or the corner point is less than or equal to B, basic feasible solution, less than or equal to basic solution, less than or equal to NCM. So in this case, what I have shown is that the vertices or the corner point is equal to basic feasible solution. Okay, and why they are equal? Because this is non-degenerate case. Non-degenerate case means that basic variables that we have found in this question, they all are not equal to 0. Whenever the basic variable is also equal to 0, then we will see that this will be strict inequality will hold. We will do one more example to ensure that why this strict inequality hold. Now let us come to this case. Basic feasible solution is always less than or equal to basic solution. We can see we found total 6 basic solution, but basic feasible solution are only 4. So obviously they are less. They may be equal if all turns out to be equal. So this hold. And NCM, this question, why NCM is less than or equal to BFS, we'll see this again in an example coming up. So let us first take an example to explain this, why vertices are strictly less than BFS, or we will consider next example on degenerate basic feasible solution. Now in this problem, I want to find basic solution, identify BFS, degenerate basic solution, and then I want to show the correspondence with the graphical corner point. So in this question, you can see that we already have an equality system, but actually this x3 and x4 act as a slack variable only. They are not appearing in the objective function. So I can also write this as x1 plus x2 less than or equal to 3, x1 minus x2 less than or equal to 0. And in the objective function, this is simply maximum z equal to 2x1 plus x2. And so treating this x3, x4 as slack variable, we can do the graphical method. And here I have found the basic solution. So in the basic solution, we can see that there are 2 constraint and 4 decision variable. And we see that the coefficient matrix A will have order 2 cross 4. So we are going to choose 2 basic variable knowing that the rank of A is 2. So select 2 basic variable and select 2 non-basic variable. So with the usual process, I get these basic solution. So we got 6 basic solution, that is NCM. But how many are basic feasible? For this one is non-basic feasible because there is a negative sign here. So basic feasible solution are 5. This is 5. And I want to see how many are vertices. And then I also want to identify what is degenerate BFS. So we have this as basic feasible solution. These are basic feasible solution as well as basic solution, obviously. And for degenerate, these 2 are basic variable, they are not 0. So this is non-degenerate case. But in this case, we see that x1, x3 are basic variable and x1 is coming out to be 0. So this case is degenerate basic feasible solution. Even here x2, x3 are basic variable, but x2 is coming out to be 0. This is also degenerate basic feasible solution. In this case, x2, x4 are basic variable, x2, x4 are non-zero, so this is fine. This case is non-degenerate. The last case, x3, x4. x3 is 3 and x4 is 0. So this case is also degenerate basic feasible solution. So we got 3 degenerate basic feasible solution and 2 non-degenerate basic feasible solution. Now let's see its correspondence with the graphical corner point, and then we can also understand what is the value here we are going to get. In the graphical method, so now I am going to draw the constraint. First constraint is saying x1, x2. So it cuts at the point 3, 0 and 0, 3, and the region is lower side. The second constraint is x1 minus x2 less than or equal to 0. So draw the constraint x1 equal to x2. This is x1 minus x2, and because it is less than, so it is upper constraint. In this case, we see that the region is this one. And the corner point that we have found, this corner point is 3, 2, 3, 2, 3 by 2. This point is a 0, 0. This point is 0, 3. Now we got 3 corner point. These are 3 corner points, but we have got 5 basic feasible solution. In the previous question, we got same number of BFS and same number of corner point. But here we got 5 BFS and we got 3 vertices. So this vertices we got is 3. These are 3 vertices. So that is why we said that this is strictly less than. Now let's see how they correspond to each other. In the first case, when I say this is 3 by 2, let's call this point as A. And here this is the point A. We can see this x1, x2 is 3 by 2, 3 by 2. I have written here the order of the solution as x1, x2, x3, x4. In the second BFS, let us call this as B. The second BFS, x1, x2 value is 0. So this is here, this is 0, 0. You can also see that this 0, 0 value is here. So this is also the same point in the BFS. This may be a different point. So I'm going to call now B, C, D, E. So this is E point in BFS, but this corresponds to same point in the corner. This is 0, 0. You can see the whole solution is actually the same, but it appeared from a different cases. It comes from different cases. Now look at the point C. In this C, we got x1, x2, 0, 0, and still we got the same solution 3, 0. So even the point C correspond to the same corner point. Now look at the last D case. In the case D, this is 0, 3. So 0, 3 is this case. So that's the point D. So we see degenerate basic feasible solution correspond to one corner point. And this correspondence is not 1 to 1. For non-degenerate, you can see this non-degenerate is this one. This non-degenerate is this one. This is unique correspondence. But for degenerate, we have many basic feasible solution corresponding to one corner point. So that is why this strict inequality holds true in this question. Now in this problem, as we can see that we need to determine optimal solution for the following LPP by enumerating all the basic solutions. So here I can see that there are 4 decision variable x1, x2, x3, x4, and then I also need to introduce 2 slack variable. So after introducing slack variable, the coefficient matrix that I get is this. So I am writing now the coefficient matrix in this form. The coefficients of x1, 1 minus 1, the coefficient of x2, that is 4, 2, coefficients of x3, minus 2, 3, and the coefficient of x4, this is 8, 4. And then I am going to add 2 slack variable also. The first slack variable is in the first constraint and S2 is in the second constraint. So that gives me 1, 0, 0, 1. And this A matrix is multiplied by the coefficient, by the decision variable capital X, and then on the right hand side we have B. So capital X here is the decision set variable. So x1, x2, x3, x4, s1, s2. I write in the same order in which I have considered these into the coefficient matrix. So this is what we have called it as coefficient matrix. And now on the right hand side, that is B. So B is the right hand side, that is 2, 1. So once we take an AX equal to B and considering that we have S1, S2, we get back to the system when this inequality system is converted into equality system. Now I want to find all basic solutions. So if you look at all basic solution, the order of the coefficient matrix is 2 cross 6. So there are 2 rows and then there are 6 columns. So that means total how many cases can I make? I can make 62 cases. And if I look what is 62, this is 15 cases. Now as 62 is equal to 15, so we see that we have to make 15 such cases which I have made here. But we notice that these cases are as usual as I've done in the last examples. You can take some of the basic variable and the other take value 0. These are non-basic variable. So put them into the reduced system and you can find out the solution. And we can also find the corresponding value of z. Now you can see that there are some negative values appearing. There are positive and non-zero values also appearing. There are some degenerate solution also coming up in my system. You can see these two solutions as a whole, they are same, but they are corresponding to two different sets. So now I want to see my inequalities again. We have started from NCM. This is less than or equal to basic solution. It is less than or equal to basic feasible solution, and it is less than or equal to number of vertices or the corner point. Now we can see this one. First, basic solution and basic feasible solution. This is equal or it may be less than. As you can see that there are some negatives, so this is not a BFS, but yes, this is basic solution. Similarly, basic feasible solution to vertices. You have more number of basic feasible solution because you can see that these two will correspond to same corner point. They will correspond to same corner point, but they are two different basic solution because they come from different cases. And now let's look at this case. We have started from 15 cases in this question, but we notice now carefully this part x2, x4. This is not a part of basic solution. I have to exclude this. So this is not a part of basic solution. Effectively, I have only made 14 cases. Now look at why I have written this as not a part of basic solution. My initially system is Ax equal to b. And in this case, whenever we select the basic variable, so once you have selected basic variable and non-basic variables, the system get reduced into b, xb equal to b. And this is what we are trying to solve. So in this particular case, I have taken x2, x4 as basic variable, and my non-basic variables are x1, x3, s1 equal to s2. This is equal to 0. This is what is written here. Now, corresponding to this, what is a B matrix? If I look at from this column x2 and x4, so corresponding to x2, x4, this is 4, 2, and then I have 8, 4. This multiplied by the decision variable, corresponding decision variable, that is x2, x4, and my right hand side, that is 2, 1. Now, if I want to solve this system, you can see that these two columns are linearly dependent. They are just multiple of each other. Second column is twice the first column, or if I write this into the system of equations, this is what it becomes. 2 times x2 plus 4 times x4. This is equal to 1. Now it is not possible to find the solution of this system because the determinant of the matrix B is a 0. So we have here 16 minus 16. This is equal to 0. And from the matrix notation, we can only find the solution when xb is B inverse multiplied by B. So that means B inverse should exist. And this will exist only when the determinant of the matrix B is not equal to 0. But in this case, determinant of the B matrix is equal to 0. So that means we can have this basic solution as less than NCM. This can also be possible. It will not exceed NCM, but it allows us to have the upper bound. NCM is the upper bound, but basic solutions are not always equal to NCM. Now let's look at this problem. Consider the following LPP maximization of this subject to two constraints, and we have decision variables x1, x3 non-negative. But the x2 decision variable is unrestricted in sign. This is what is written in the problem. x2 unrestricted in sign means we do not know whether it is non-negative or it is non-positive. So once, and we need in the decision variables should be non-negative for considering into basic feasible solution for any linear programming problem. So to avoid this situation, say for example, x2 may take us value as 7. So suppose it is a positive value. I can write this as 7 minus 0. So this 7 individual is non-negative, 0 individual is non-negative. So I am writing x2 as subtraction of two non-negative decision variable. This plus and minus is just a notation. Or suppose x2 take the value minus 7. In this case, I can write this value as 0 minus 7. In this case, give this value as x2 plus and 7 is x2 minus. So in both circumstances, that means whenever x2 is unrestricted in sign, I can write this as subtraction of two non-negative decision variable. So this is what has been asked in the problem. Show that a basic solution cannot include both simultaneously. So now let's first convert this constraint into the equality system and include this x2 unrestricted in sign with these two replacement. So this x2 will be replaced as x2 plus minus x2 minus 9x3, and then I have to also include a surplus variable equal to 4. In the second constraint, I got x1 plus x2 plus minus x2 minus. So this replacement I am using for x2 as mentioned in the problem, plus 4 times x3 equal to 10. Now let's look what can be the coefficient matrix. So I want to write this into this system. So the coefficient matrix can be 6, 1. So here let me to first write down all the decision variables. So these are simply the decision variables. We have in total 5 decision variable and the constraint are 2. So the order is 2 cross 5. So this is 7, 1. This is minus 7, minus 1, minus 9, 4, minus 1, 0. So we see that this is x2 plus and x2 minus coefficient. They both are linear dependent. As we can see that the first column is a multiple of second column with a minus 1 sign. So the similar situation arrived as it was arised in the previous case. We are supposed to make 5C2, that is 10 cases. But because of this case, so whenever basic variables are x2 plus and x2 minus, so this will correspond to the basis matrix as 7, 1, minus 7, minus 1, and we can look at the determinant is equal to 0. So for this case, solution does not exist, and we can also see that whenever we have reduced ax equal to b to the system bxb equal to b, this should be solvable. To have this solvable, that means we have considered into this form, and the determinant of b should not be equal to 0. So this case, this choice will not come x2 plus and x2 minus. So there are effectively 9 cases that we have made for basic solution. So that satisfies that this basic solutions are always less than or equal to NCM, and it also addressed to our problem that show that basic solution cannot include both x1 x2. It cannot be included because the determinant of the matrix B is equal to 0, or we can simply say that these two columns are linearly dependent.